Hello. It was Friday afternoon, around 4 p.m., when I saw a green build on our CI server. I knew that I have to deploy it to production before the weekend. I also had really strong gut feeling that it's a bad idea. It wasn't a mere superstition about Friday deployed kittens. See, this one is quite afraid. A couple weeks before, I managed to break production. I had to revert my deploy, and I had to stay late after work. So I knew the risk. Still, I also knew that I have to deploy it. You may wonder why I wanted to deploy anything on Friday, especially that late. You may think, why was it so important to do it? And what was the whole project about? I'll answer those questions right away, but before that, let me introduce myself. I'm Maciek Rzasa, and I live in Rzeszów, southeastern Poland. And at TopTal, where I work, I'm in the spearhead of the big initiative of migrating the whole technical infrastructure to service-oriented architecture. I'm in the billing extraction team. After work, I really like sharing knowledge. That's why I'm here. And really, after work, I really like the most important stuff, but it's out of scope of this talk. So let's get back to the business. What's the TopTal platform? What is the architecture that we are tackling? TopTal platform is our main application. It handles most of our business domain. It's a standard Rails application. It has over 1 million lines of code. There are hundreds of engineers working on this app every day, and we have thousands of users relying on this application. So I have to say that it's a monolith, and that it is a majestic monolith. And from this majestic monolith, my team, the team when I work at, tries to extract a cohesive part of the whole domain. We try to extract the logic related to billing and deploy it as another service. That's our task. So how do we tackle it? How we approach this? We have to keep in mind that there are hundreds of other people working, actively developing this app. So we had to do it in a safe way, and so we had to do it incrementally. The first step that we did was extracting billing logic into a Rails engine and rely on the direct method calls whenever platform wanted to access billing logic. The next thing was to actually add networking, to actually add external calls, but while still keeping the billing inside the same Rails process. So let's take a look. We added Kafka for asynchronous API. It's really interesting, but unfortunately out of scope of this talk. And we added HTTP interface for synchronous API, and that's the gist of this talk. And to make it safe, we added two safeguards. The first one was an HTTP feature flag, so we were able to switch on and switch off this experimental REST API whenever we wanted without deploy, and for a fraction of the whole traffic. And another safety feature was a fallback. So whenever HTTP call failed, there was a client error or server error or timeout, we fell back into a direct call. So the user of the billing engine was still able to get the data, even though there was an error. So if we are to look at the triad that I mentioned on the first slide: monitor, fix, deploy. I have to say that we started with the last part, with the deploy part, because besides the CI check that are very common and that are really complex at TopTal, and besides easy deploy and reliable rollback, that's also very popular, we introduced a safe environment when it was okay to, if our external call failed, because we have a fallback, and we had feature flags that allowed us to switch on and switch off the experiment whenever we needed. How did the extraction look like? At the beginning, we had two models at the platform: product and billing record. Product was meant to stay inside platform, and billing record was meant to be moved to billing. So after the extraction, it looked, on the platform side, it looked like this. We had product, and instead of has many relationship from Rails, it had a method that was calling a special service that accessed billing data. And we have a plain old Ruby object, billing record, that wrapped the answer from the billing record and was enriched by a reference to a product, and this reference was got from the database. All the magic, all this, both the safeguards, the fallback and the feature flag, was encapsulated inside the billing service. So that was our approach to isolation, and we developed it, we deployed it, and we enabled it for a fraction of the traffic, and we failed miserably. Let's try again. Maybe this one it works. No, it doesn't. We enabled it for a small fraction of the traffic, 10 or 20%, and the performance was abysmal. We weren't able to make it right, to make it working, and we knew we had to optimize it. So it's a standard setting, right? We have a small API call, so we sit down, we check on New Relic, we check locally, and we optimize it, and then next API call and next API call, right? So that's not something we did. We decided that REST is not flexible enough for us. We decided to make a very radical move in the middle of this big refactoring that's billing extraction, and in the middle of adding the actual networking calls, we decided that we have removed already implemented REST API, and we have to switch to GraphQL API. So we added the GraphQL part. We added another layer of feature flags, so we were able to switch between REST and GraphQL on the fly, and we were able to enable GraphQL only for a fraction of the traffic. And of course, we added fallback to GraphQL requests so that we can control, we can reply to our callers even if we have GraphQL error. And again, we were at the point when the first reflex would be to start coding, right? We had a full specification of the REST API, and we knew we had to move it to GraphQL. So let's just take endpoints one by one and code, right? Again, that's not something that happened, because before we jumped into optimization part, we decided that we have to enhance our monitoring. To avoid flying blind, we enhanced the standard monitoring we had, namely monitoring of errors in rollbar Sentry and monitoring of performance in New Relic. We added custom request instrumentation. So every time we sent a request to billing, we were logging method name of the billing query service, arguments of the call, stack trace, the source of this call, the response time, and if needed, error that happened. that let us not only identify slow calls using that we have slow calls using elapsed time, not only identify that we have a lot of calls just by counting the logs, but also identify which methods are frequently used and reproduce those slow calls locally using arguments, and also identify the actual users and see why this method is used and why this method is slow using the stack trace. That was really powerful. And so because of that, we had the first part of the triad, monitor. And it let us prioritize the GraphQL migration according to the performance needs. We identify three main performance indicators of performance issues. The first one were 4 to 9 HTTP errors on rollbar. Another one were a lot of entries in logs or slow responses in logs. And another one was a habitual New Relic monitoring and identifying performance spikes in the billing service. And with those two parts, good monitoring and safe deployment, we were able to jump into fixing the performance, into optimization. And I'll tell you about our effort in optimization. Please treat this, you can treat it as a series with separate seasons, with separate episodes that are loosely connected. So it's more like Friends than The Crown. The first thing that we tackled was a flood of requests that we noticed in our logs. So a single view or single job in the platform was generating multiple requests to billing service. There could be thousands of requests sent by a single view. You can imagine how slow it was, and you can imagine that it was killing the billing service. Why did it happen? Let's see at this example of a background job. We were choosing products, and then in batches we were doing some business logic call. Inside this business logic, we were accessing billing records. And when we were accessing billing records, we were querying the billing query service. So if we had thousands of products here, we were making thousands of billing queries here. So it was quite similar to N+1 problem with the database when you send multiple database queries in a loop, right? It was exactly the N+1 problem. How we tackled it? We weren't able to use standard N+1 anti-N+1 techniques, so we had to implement something in our own. And what we did was moving data loading one level up. Instead of loading the data inside the model, we cached them before the data was needed. So for every batch, we run this caching method that did as follows. At first, it queried the billing query service. It indexed the records by the product ID, product GID that was used, and then we were iterating over products and assigning those billing records to every product. And because of that, we were making only a single request to billing query service per batch. We started with 1,000 of requests, and we ended up with 10 requests because we were making the batch of 100 products. It was quite a good result, and it was acceptable from performance standpoint. So what we learned was that if we send a lot of requests that originates in the same place, we probably should go one level up and preload data from the external service. Next episode, it's quite similar to the first one. Instead of n+1 billing queries, billing requests, we had n+1 or n database queries. Why was that? Let's take a look at this business logic example. We were fetching data from billing query service, and then we were iterating over billing records. And every time in every iteration, we both needed a record and a product. And to fetch the product, we had to access the DB. So again, if we had n billing records, we had n requests to the database. Not very good, not very performant, right? So in this time, we decided to enhance the query service itself, because we actually received the product that we needed, right? So what we did was indexing the products first, then we were requesting the query service, and finally, when we had the billing records, we were iterating over them, and we were assigning the products as needed, using the hashed values, the hash by ID. If you think that it's similar to a hash join known from the database, you're right. And that was actually something really interesting to see, that an algorithm that's from decades used in the databases now was very useful on the app level, when we decided to use a compound data source, not only database, but also the external service. We tackled those first problems, and then there was another one. We were fetching too much data from the billing query service, because we aimed to have a small and generic API. That's why we were putting in the REST response every field that could be probably needed on the platform side, and every association that could be needed on the platform side. We ended up with almost 40 fields and 3 or 4 association loaded, with probably tens, dozens, or hundreds of records, while we often needed only a couple of fields. So we had to fetch them all from the database, then serialize it, and then deserialize it on the platform side. It was very slow, and we consumed a lot of memory. To make it even worse, part of filtering was done on the server side, on the client side, instead of the server side. We were loading all those records to the platform, and then we were calling regular Ruby select to filter them. So what we did, we re-implemented this in GraphQL, and this was the moment when GraphQL really shined, and when we really leveraged the power of it, and when we were very happy that we decided to use GraphQL instead of REST, because we were able to use its flexibility on the consumer side to build queries that were fetching only what is needed without changing anything on the server side. While we implemented types on the server side, we were able to optimize many calls on the client side without touching the server. So this example, we fetch only 4 fields instead of 40 fields. And also we implemented a couple of filters on the server side. So we were fetching only data that is needed. And it was really promising. And at this point, we were up to speed with this migration. And actually, that task was implemented by me, and I was really happy about it, because it was a work with a really short feedback cycle. I was taking a task, I was analyzing how to improve performance, implementing it, checking locally, then waiting for reviews, merging, enabling the feature flag, and then seeing how the stats improve on New Relic and in our logs. It was great because I actually was able to very quickly see the results of my work. So it was the same in this case. I developed it, I merged it, I pushed it to production, I enabled the feature flag, and I was waiting for the stats to get better. Quite happy that I did such a significant improvement, possibly. And what happened instead? By the way, do you remember last summer in the Northern Hemisphere? Do you remember what was the hottest day of this summer? I do. It was 28th of July. Why was that? It started quite good. I deployed my changes to production, and I was checking Slack, and on the public channel, a developer said that there are issues with Sidekick workers, and that they consume a lot of memory. And I thought, oh, poor infra guys, they'll have a lot of work with that. And another developer said that there is a problem because staging deploy fails. As a last stage of our CI pipeline, we deploy to staging, and it's the last automated step, and then we can decide to deploy to production. And what was next? I got direct messaged that it was my build that broke the staging. And even at this stage, I was pretty sure that it wasn't my build. I was, of course, checking it to see why it happened, but I was rather checking the hypothesis that it was caused by someone else from the other side of the company. And what happened next? One of our internal users, meaning that the business people that are earning money using our platform, told us that something is wrong with the platform, and I still thought it wasn't my build. And then another internal user just said, oh, the platform is down. And it was about when the business hours started in the US. It was bad. I realized that it was my build, and I started sweating. It was the hottest day last summer. What we saw on the stats. So regarding the CPU usage on the background jobs, the spikes were at 20 times bigger than a normal usage. On the right-hand side, we can see the normal usage after we fixed the issues. And here was the outage. It was 20 times as bad as in usual times. And the last graph is with memory. It was about 50 times worse than in usual. And to make it even worse, we had Postgres queries taking a minute. It was terrible. But then happened two really good things. The first one, at the same day, before I was even able to realize that it was my build, infra team was able to revert it and deploy the correct version. Then they assisted me to fix the issue, to revert my build on master, to make the master green again, and to deploy the reverted version. I had to stay longer hours, of course. I had to monitor production, but I was able to fix it with their assistance and to make it working again quite quickly. And another good thing happened the next day. My manager approached me on Slack, and you may imagine, or you can think about a manager approaching you in this kind. The good scenario is a really polite person asking you open questions until you admit that you failed. In the best case scenario, It's yelling and pointing fingers, and you're trying to defend from being fired, right? And of course, that's what didn't happen. My manager approached me, asked me if I need anything, and told me, man, good job. And that I was really surprised because I broke production. And he explained me that yeah, breaking production was a problem, but it was fixed easily, and I stayed to monitor it, and it's all okay. And I should just focus on fixing the issue, and that was great. That was another part of this safe deployment environment. You could fail, and it's okay. You should just fix it. So, what actually did go wrong? I was doing a small refactoring on the REST branch of the client. I added parameter slicing to make it safe, and I allowed only one parameter. Then on the server side, we had billing record method that was fetching billing records, and it accepted a couple of parameters, and it was building a query. The issue was that if none of those parameters was present, it was calling just all on billing record scope, on billing record class. So I over-sanitized parameters. And if someone was asking for billing records for a single client, nothing was sent to the billing service. And because of that, with every request to client billing records, we were fetching every billing record, and with them, we were also fetching all the related tables, and that was millions of records that was fetched from database to memory, and that was pushed through the network, and that was something that killed our servers. How did we fix it? We added safeguards both on the client side and on the server side. If the parameter list is empty, just return nothing. And of course, I fixed this slicing. To our defense, the most popular query language you have behaves the same. If you forget to add a condition to where, you will fetch entire table from the database. Even worse, if you forget to add where clause to your delete statement, you will remove the whole table. That in most cases is undesirable, right? Let's get back on track. We fixed the issue, and what happened next is it is all shown on this graph. It's a neural graph. It's before the failed deployment. Here happened the failed deployment. We had a gap when billing wasn't serving any HTTP traffic because we switched it off. And then it was after the fix when we had not only faster responses, but also more reliable ones without those spikes of response time. So we did it with query customization and underfetching, and with filtering on the server side. What we really learned this time, what I really learned this time, is even if I trust CI and my reviewers and myself, I should test manually. Because in this case, I relied on CI. We had this line in our pull requests. In every pull request we sent, we have a question, how to test this? And I answered, trust the specs. What I really should answer was, okay, try to play with console with this comment and this comment and try to fetch this data like this. And I believe that if I tested it for 15 minutes, I would have been able to detect this abnormality, but I didn't. And now I know that I should really test manually. That was a really intense episode, right? Let's move on. it wasn't the last one. The next problem we were trying to tackle, another problem we were trying to tackle, was that we had a single field that was really, really frequently used, like 1,000 hits per day, and sometimes, and to make it worse, there were huge spikes. So during 1 hour, it was used 800 times. It was a little bit too big of a usage. It was a certain date, and we decided that if it's a single field and we can't really preload it in the classical way, we should preload and cache it in a smart way. So we decided to add this field to Kafka event, then use this field to build a read model on the platform side, then run migration to backfill the data, and then start using this read model. And that was a really smart plan. It was good engineering, right? It was according to current standards. I started to implement it, and I was very happy because it was really interesting. And then Samuel, our coworker, our teammate, came and said, "Folks, I think that we may find this data on the platform side." Samuel, as you can imagine, Samuel has a really good domain knowledge in the billing side. I was a little bit angry because he was proposing to do something else, and I really wanted to do it with Kafka because, it's fancy, and when you do it with Kafka and you build a projection on the client side, it's something that you can read in books and then you can make a talk out of it. Yeah, that would be great. But what we did instead, we talked to domain experts, to both developers and product people. We ran some checks on the databases to compare those two fields on the billing side and on the platform side. And we decided that we really can use this field from the platform database. And with this simple query, we replaced the original billing call, and we replaced our grand plan to use Kafka. And we did it in 2 or 3 days instead of 2 weeks. And that was a huge gain. And to make it even better, this free-line solution is definitely easier to maintain that big Kafka pipeline. And when we deployed it, it really worked, and it was great. So what we learned here is that fancy technical solutions aren't always the correct answer. Sometimes we need to leverage the domain data and try to find the solution in the domain field, not in the technical field. And we still had some issues that happened from time to time. This time it wasn't usage in the logs, high usage in the logs. This time it was 4 to 9 HTTP errors in rollbar. It happened every Sunday evening, and it was pretty strange because we weren't able to reproduce it locally. We determined where it happened, but we had to check it in production. What was the culprit? We were sending weekly reminders. We were scheduling and sending weekly reminders every Sunday evening to our talents. And during scheduling the reminders, we were using some billing data. So we used a standard solution. In the scheduling code, we used batching and preloading and called it a day. We were sure that it was enough. So we deployed it, we developed it, we merged it, we deployed it, and we waited for Sunday. And in the Monday morning, we saw the error again. Why was that? Well, we were not only scheduling those reminders, but also calling those reminders. And we didn't want to act on the stale data when sending reminders, and we had to ask billing again if the reminder is still valid. That's why we had floods of billing requests when the reminders were actually executed. So what was the solution here? We knew that it may happen, but we calculated how many talents we are. We calculated that the reminders are sent in their time zones, so we divided it by 24, and then we decided that it's okay because we will handle this load. What we didn't check was again the domain part. So 25% of our talents live in the same time zone. And the second most popular time zone is inhabited by 50% of our talents. So when Sunday evening came in those two time zones, we were overloading the billing service. We couldn't preload the data here because every reminder was run in a separate Sidekick job. We couldn't move the talents to disperse them uniformly around the globe. So what we did was moving the reminders. We decided to add a small jitter of 120 seconds to the reminders, to scheduling the reminders, and that would let us to spread the load, and because of that, avoid this big spike of requests at 5 p.m. So we developed it, we tested locally, we checked that it was scheduled properly, we merged it, we deployed it, we waited for Sunday, and on the Monday morning, we saw the same error. Why was that? Again, the domain knowledge, we overlooked one more reminder. So it was a simple fix. We did it quickly, we merged it, we deployed it, we waited longer for the Sunday evening, and when the Monday came, we saw the same error. That was frustrating. What was the issue? We were sure that we scheduled the Sidekick job properly, but apparently they weren't executed as we scheduled them. Instead of being executed in 120 small buckets, they were executed in about 8 bigger buckets, causing those overloads. The issue was that Sidekick had quite low resolution in executing scheduled jobs, and it was polling credits every 15 seconds or 30 seconds. And it was scheduling all the jobs that were older than this. So yeah, instead of 120 small buckets, we had 8 big buckets that was caused this overload. So we went enterprise this time. We took Sidekick limiter that's inside Sidekick Enterprise Edition, and we implemented proper rate limiting to allow, let's say, 10 requests every second. And we tested it, we deployed it, we waited for Sunday, and on Monday morning, there was no error. It was great. Look, it took us 4 weeks to fix it. It took us 4 weeks to optimize it. We were able to do it safely because we had this safe deployment structure, and with every 4 to 9 error that happened, we were using the fallback. So we were able to go diligently and test our solutions, even though we weren't able to test them locally. And it was during this optimization when I saw a green build on Friday, and I knew I had to deploy it to production, and when my gut felt very strongly that it was a bad idea, and when I decided that it's safe to write deploy bot, deploy platform to production, and I succeeded, and I went home, and it was Friday as usual. I hope that now you understand why it was so important to deploy before weekend, and that you follow my reasoning here. And when I was doing a fact check for this talk, I realized that it wasn't as I remembered. It wasn't just a single Friday deployment. Actually, I did two of them. The first one was in the first week of this optimization saga, and the last one was in the last week of this optimization saga. I did two Friday deployments, and both of them were around 4 o'clock, and both of them succeeded. That was great. So let's recap. What helped us in this optimization journey was those three parts. The first one was proper monitoring. We had the standard monitoring, errors and performance, but besides that, we also had our custom request implementation that allowed us to pinpoint the hotspots to determine exactly what was the root cause of performance issues. We had our deployment structure that was really safe. We have really good CI checks. We have easy deploy with reliable rollback. And besides that, we added custom safeguard that let us use the direct calls whenever the remote call failed. And we have feature flags that allowed us to switch on and switch off the experimental features without making a deployment. And with those two pillars, we were able to actually fix the performance of our service by applying preloading and caching, by moving filtering to the server side and fetching only the data that's needed, and by spreading the load. And when you take a look at this list, I believe that it's not surprising to you. I think that you know those techniques and you probably applied them. So what is the whole point? Why do I bother you talking about this here? What's so important that I decided to speak about it here? Let's see about if you don't follow, if you think that you haven't seen them, let's see how similar they are to something that we already know. So preloading to avoid n+1, that's something that every ORM does, right? We did it for GraphQL. Regarding up-level hash joins, we learned it from the database world. Server-side filtering is something really similar that we all did by moving Ruby finders to active record queries, right? Using local data is like a browser performance primer. You want to have a fast HTTP application, avoid HTTP queries. Under fetching is something standard in SQL, and about spreading the load, I read about 10 years ago in a blog post about YouTube architecture. So what was crucial here was that we took those known techniques and we applied it in a new setting. So, and why didn't we do it right from the beginning? Why did we need this journey to learn it? The answer is threefold. It's about learning, simplicity, and trade-offs. First of all, we realized that during refactoring, it's really easy to overlook performance issues when you just stare at the code. And on local machine or even on staging, it is hard to recreate the production traffic to see how the changes behave in the traffic with the production shape. That's why we needed to make production experiments to learn how our code behaves in production settings, and then to fix the performance issues. The simplicity. We started with a boring, simple, and generic solution. We started with small REST API that was giving big generic responses. And then we slowly went to something more sophisticated. We implemented the GraphQL API when it was needed. We wanted to avoid over-engineering just for the sake of over-engineering, because we wanted to make the simplest thing that could probably work. And the last thing that I want to mention are trade-offs that were all about this optimization saga. Let's take a simple example. When we were implementing the jitter spreading the load and we were discussing it with one of our feature teams, they were a little bit worried about it, because they said, when we query billing, we want to get the response instantly. When we send a reminder, we want to send this reminder instantly, not within the 2 minutes from when we plan to send it. And we had to convince them that it's impossible. We had to convince them that it's a trade-off between sending all of them or sending them quickly. And that's why we did it. That's why we did it incrementally. So what was it all about? It was about determining the known patterns in a novel setting. It was about understanding those trade-offs that I mentioned, and it was about applying knowledge that we already had in our current scenario. So I shared our story. I told you about mistakes that we made. So now you don't have to make the same mistakes. Instead, please go back to your work and do your own mistakes. But then please get back to a conference like this and describe them so that we all can learn from you. And if you want to do a quick sanity check, if your environment helps you learn and helps you learn from your mistakes, just think if you can safely deploy on Friday. Thank you.